All right, we're going to cover the underdamped voltage response now, and we'll probably also get to critically damped before the end of this video. This is the one where we have alpha squared less than omega naught squared. This is the one where S1 and S2 are complex numbers. All right. So in this case, S1 is going to equal minus alpha plus the square root of alpha squared minus omega naught squared. So what's underneath the radical is complex number. And S2 is going to be minus alpha minus the square root alpha squared minus omega naught squared. Okay, for this class we're going to use J for the square root of negative 1. We're not going to use I. Hopefully the reasons for that are kind of obvious because it's already been taken. And I'm going to make a substitution here. I'm going to call omega sub d is equal to the square root of the stuff that's underneath the radical, but let's take the absolute value of it so that it's positive. You could just reverse those if you wanted to, but anyway, it's the absolute value of what's underneath there. This is called the damped radian frequency. Okay, so our solution, our general solution, you know that is V equals A1 e to the S1t plus A2 e to the S2t. And what we're going to do now is we're going to substitute in for our S1 and our S2 up here. So this is going to be A1 e to the minus alpha plus omega sub d, times j t. So I substituted in for S1 and S2. Omega sub d is what's underneath the radical, and I factored out the j. Okay, so that's that one right there, and then plus A2 e to the minus alpha minus omega sub d j t. All right, so we've plugged in for our S1 and our S2. I'm going to simplify this a little bit. You can separate these exponentials here, and I can have A1 e to the minus alpha t e to the j omega sub d t. All I did is change the order, put the j in front of the omega sub d here, plus A2 e to the minus alpha t e to the minus j omega sub d t, like that. Okay, I'm going to factor out the e to the negative alpha t times A1 e to the j omega sub d t plus A2 e to the minus j omega sub d t, like that. All right, now we're going to introduce an identity. It's technically, I guess, a trig identity, and it's called the Euler Identity. Euler. And it's this: e to the plus or minus j theta, theta is an angle here, is equal to cosine of that angle plus or minus j times the sine of that angle. Okay, so this is the Euler identity, and we're going to use this, since it's a j angle, we're going to treat these e to the j omega d's, we're going to treat omega dt in each of these cases as if it is that angle theta. And it could be plus omega dt or minus minus omega dt over here. Okay, so let's go ahead now and make that substitution, and we end up with e to the minus alpha t, and now we're going to have A1 cosine, please understand that's a cosine there, cosine omega sub dt plus A1j sine omega sub dt plus A2 cosine omega sub dt minus A2j sine omega sub dt. There. Okay, I can simplify that a little bit, group together the cosine terms and the sine terms here. E to the minus alpha t times, let's see, I got a1 plus a2 times the cosine omega sub dt, plus j a1 minus a2 times the sine omega sub dt, like that. Okay, now this a1 plus a2 that we see right here, let me scoot that up a little bit. This a1 minus a2 and the a1 plus a2, those are just combinations of coefficients. I could make this even simpler by saying that's e to the minus alpha t times b1 times the cosine of omega sub dt plus, and now I could take all of that right there and make it one coefficient, b2, times the sine omega sub dt, like that. And that's our voltage response. In fact, that's the voltage response for this case, which remember is the underdamped case here. So this is what the general solution looks like then for the underdamped case. Now, something here you may be wondering about, this j times a1 minus a2, that is a real number. It's not real obvious. In fact, it's not obvious at all, but that is going to end up being a real number. And it kind of makes sense down here. If you think about it, these coefficients right here need to be real because the voltage itself is a real physical entity. It's a real physical phenomenon, voltage. So the voltage function has to be real. So B1 and B2 are going to be real numbers here. So here we've got this voltage function. And then if you want to solve a problem that ends up being an underdamped solution based upon the comparison of the alpha squared and omega naught squared, you start with this. This is the general solution that you start with. Then you need to figure out the voltage at 0 plus. Well, if you go back here and you plug in t equals 0, the exponential becomes 1. This cosine term is also going to be 1 when you plug in t0. This sine term, though, is going to go away. So the voltage at t equals 0 is just going to end up being B1 when you plug in t equals 0. And then the other initial condition, I sub c at 0 plus, remember you divide that by c and that's equal to dv dt evaluated at 0 plus as well. Go back here, take the derivative of this. You've got products here, so you're going to have to use a product rule to take that derivative. But when you take the derivative and when you evaluate it at t equals 0, you end up with this, minus alpha times b1 plus omega sub d b2. So this equation here, I sub c or 0, that will be given. The I sub c of 0 plus will either be given or you will be given enough information to figure that out. C should be given. Alpha and omega sub d, those are computable. Based on, if you know what the RL and C values are, you can compute those. And then these coefficients, B1 and B2, can be found in conjunction with this equation up here. So how do you approach this problem? You approach a problem, a parallel RLC circuit problem, by computing alpha squared and omega naught squared, doing the comparison, and if it turns out that alpha squared is less than omega naught squared, that's the underdamped case, then this is what your general solution looks like. And your job then, after you figure out that that's the form of the general solution, is to calculate or determine what B1 and B2 are based upon these initial conditions there. Okay, now this is the underdamped case, and let's look back here. You see what we have here is we have trig functions. We've got two trig functions, a linear combination of trig functions. This is kind of a mini Fourier series here. But anyway, those are going to be trigonometric oscillating types of functions, but then that's multiplied by this decaying exponential. So if you were to graph that sort of thing, the voltage versus time, you've got some sort of time-varying function here, and that's the sine-cosine portion of that. But then on top of that, you also have the decaying exponential that's going to do something like that, okay? So the exponential is going to decay that way. So if you were to multiply these two things together, what you would end up with is something maybe that looks like this. You can see the exponential decays over time. So I'll make that a little clearer, is it is oscillating, but the oscillations are getting smaller with each cycle, like that. And that's what you get when you multiply the exponential, the decaying exponential here, times the sine and cosine. Okay, that's the underdamped solution. We'll work some problems with the underdamped, the overdamped, the critically damped solutions here. But for right now, let's also cover the critically damped, and maybe you can see a little bit about where that comes from. So for the critically damped solution, we've got the case where alpha squared is equal to omega naught squared. Okay, so we've got this case where alpha squared is equal to omega naught squared. In that case, S1 is equal to S2, and they're both equal to just minus alpha. And the minus alpha, remember, that's just 1 over 2RC, like that. Okay, well, if you go back to our original form of our solution here, A1 e to the S1t plus A2 e to the S2t, then in that case, S1 and S2 are equal to each other. This is just going to be A1 e to the minus alpha t plus A2 e to the minus alpha t, like that. And you can put those together, A1 plus A2 together, times e to the minus alpha t. And you could even replace A1 and A2 by a single coefficient to look like that, okay? But here's the problem with this. That's just one coefficient, that's one voltage response. That's insufficient as a solution for a second order differential equation, which is what the equation of state is for a voltage. There is a theorem from differential equations that says if this is your form of your solution, then you can have a linear combination of this as well. So we could write our final solution as this, D1. D1 is just the coefficient. We skipped over C's for, again, obvious reasons. D1t e to the minus alpha t plus D2 e to the minus alpha t. So you take your solution, you multiply it by t, add it as a linear combination, and this now is a more general solution for the critically damped case. All right. Now, once again, you have to figure out these coefficients, D1 and D2. So how do you do that? Based upon initial conditions. V at 0, plug in t equals 0 here. That term goes away. The exponential here becomes 1, and we're just left with D2. And then I sub c at 0 plus divided by c is going to be dv dt, evaluated at 0 plus. Take the derivative of this and evaluate it at t equals 0, and you're going to end up with this. We're leaving out steps here, but hopefully you get the idea. And with these two equations, then, you can compute your D1 and D2 values then. All right? So what we've done here is we've covered the overdamped, underdamped, and critically damped solutions. So let's sort of summarize this. If we've got alpha squared greater than omega naught squared, then what's underneath the radical of the S1, S2 equations is going to be positive. And in that case, the voltage response is just going to look like A1 e to the S1t plus a2 e to the s2t. And that is called the overdamped. So that's the overdamped solution. If we've got alpha squared less than omega naught squared, then what's underneath the radical for S1 and S2 is going to be negative. And in that case, we've got, it's going to be a complex number underneath there. So what does that reduce to? V of t is going to look like B1 times, cosine omega sub d t plus B2 sine omega sub d t, all of that multiplied by e to the minus alpha t. And that is for the underdamped case, okay? And then we've got the other special case where alpha squared is equal to omega naught squared. And in that case, v of t is d1 t e to the minus alpha t plus d2 e to the minus alpha t. And that is the critically damped case, like that. Okay, so those are our three solutions here for the three possibilities for our voltage response. Now what we're going to do is we're going to start working some problems for each of these cases, and you'll see the process here, and hopefully all of this will come together and make a lot more sense. We'll begin that in the next video.